recap real quickly on the chemistry stuff that we already talked about. We talked about ions and ionic bonding. We talked about covalent bonding. What's the difference between the two? Who shares? Which type of bond is a sharing bond? Covalent bonding. And ionic bonding is sign of a transfer, either accept or gain what? Electrons. So when we talk about chemical reactivity, when we talk about chemistry, who are the big players in a chemical reaction? What part of the atom? Electrons. Specifically, which ones? Valence electrons. Yes? So everybody understands what an atom is. Everybody understands what an atom is made up of. Everybody understands what a valence electron is. And everybody understands that. Yes? More or less. We're not going to get, again, not going to get too crazy on all the specifics of the periodic table and orbitals and energy levels and all of that good stuff. You get to do that in chemistry. But we want to have a basic understanding of chemistry for anatomy. So we can understand things like chemical reactions of metabolism when we hit that point in the chapter. So we good with that so far? What type of bond is this between oxygen and oxygen? It's a covalent bond. And how many pairs of electrons are being shared in this covalent bond? 2 pairs. And there's an even sharing of those electrons. So watch my arms. Ready? Electrons are going to rotate around the 2 when we have a covalent bond. Pretty good, huh? Because I just had lunch. So I have energy. I had to think really hard to do this. Now, that is called a polar covalent bond. Is it? No. It's called a nonpolar covalent bond. How come? What's polar? Ooh. Yeah, that wouldn't happen evenly in a polar covalent bond. We'll actually have molecules that have a slightly negative and a slightly positive end because we don't have equal sharing. So that's what we're going to pick up today. So polar and nonpolar molecules, even though they're covalent bonds, even though they are on the whole a neutral molecule that is formed, sometimes we don't share nice and we don't share equally when we come together with another atom or element. So carbon dioxide, which is what? 1 carbon and 2 oxygens, shares nice, shares evenly. It's a covalent bond, and how many pairs of electrons are shared between oxygen and carbon? 2. Good. Now, when we draw it out, we see that it's a nice symmetrical linear molecule because of the way it shares. So it does this. Yes? Now the confusing part's going to start. You ready? Some covalent bonds don't share equally. This guy down here doesn't share equally. Oxygen is a tad bit greedy. So you ready? I don't know if I'm going to be able to do this. So we have electrons here. Yes? See what I'm doing? So I make more arm motions around oxygen because even though we're sharing pairs of electrons, and how many pairs are we sharing between hydrogen and oxygen in this molecule? We're sharing one pair, hydrogen and oxygen, the other pair, hydrogen and oxygen. Everybody's happy, everybody's neutral, but because of something called electronegativity, the electrons tend to hang out a little bit longer around the oxygen than they do around the hydrogen. Yes? See what happens? It's good arm exercise. Does that make sense? So now we have a covalent bond, but it's not a nonpolar covalent bond. It's a polar covalent bond, creating two separate poles in our molecules. So think of the Earth. There's two poles on the Earth, right? There's a North Pole and there's a South Pole. In these molecules, there's a slightly negative end or pole, and there's a slightly positive end or pole. And water is a polar molecule. Now, what's that have to do with anything? Well, because water is a polar molecule and it has a slightly positive and a slightly negative end, it has a slight attraction towards things that have an opposite charge on its opposite ends. So at the oxygen end, where I'm slightly negative, I tend to attract what? Positive things, or slightly positive things, towards that end. And what do I attract towards my negative end? Or slightly negative end, slightly positive things, or positive things. And this is going to help water be a very wonderful solvent. What's a solvent? Things I dissolve other things in. So in salt water, for example, the solvent in that solution is water. And the other term you need to know, solute, would be what? Salt. The thing I'm dissolving in the solvent. One of the things that we're going to talk about is hydrogen bonds. We call them weak bonds, but they're extremely important bonds or attractions. Remember, that's kind of the same word when we're talking chemistry. In biological systems, especially in human biological systems. So those weak bonds, those hydrogen bonds, those attractions of hydrogen to other things, and in water, what do you think we're doing here? With that slightly negative and slightly positive end of water, what do you think that each of those molecules are going to do to each other? They're going to attract each other, pull each other close. So because of that, water, because of that attraction, that hydrogen bond or attraction, we create something called surface tension. Did anybody ever heard of that stuff? It's the reason why you can't jump off the bridge over the Kennebec River, even though it's in water, and survive. Why? Why can't you survive? You see all those guys dive off those cliffs all the time. What's the point? I can do that, right? Why can't you survive if you dive off that bridge? No, it's pretty deep, actually. Ships go through there. Yeah. Because of the surface tension, it would be like hitting that. Because of the surface tension created by the hydrogen bonded, the hydrogen molecule attraction, that hydrogen attraction to the slightly negative end of water. So it's the ever see one of those things? Yeah, they're fun to catch too. That's the reason they can do that, because water has a high surface tension. That might be a problem sometimes, especially when we start talking about gas exchange in the lungs or exchange of nutrients and wastes in places like the kidneys or the digestive system. But water is a very wonderful solvent. Water has a very high surface tension, but water also, because of the fact that it has a high surface tension, it takes quite a bit to move it from one state of matter to the next. Do you know what I'm talking about? Think about water. Can it be the 3 states of matter that we talked about? Yeah. So I can take some water and I can put it in the freezer, and what do I get? A solid. Magic. And I can take that same water and I can put it on the stove and apply heat to it and turn it into what? And turn it into a gas. But because of the fact that that attraction is there and that high surface tension is present, what we're going to see is when we take water and push it to its next state of matter by applying heat, going from a liquid to a gas, we're also going to take a lot of that heat away with us. So water has a very high heat of vaporization level. Now, is that good? Good for us as living human biological systems? How come? Oh, yeah, the other day, especially hot, muggy, what happens to you? Happens to me a lot these days because I'm getting old. Sweat. What's the sweat doing for me? How? Yeah, water, again, because water has a high heat of vaporization, and you feel it more when you stand in front of something that's going to cause that to happen at a faster level. Anybody? A fan. So if I move air across the water, I break up some of that surface tension and I allow the water to do what? Evaporate at a faster rate. So you can actually feel the cooling effects when you're sweating and you stand in front of the fan, you go, ah. You sweat all the time. Did I tell you this already? Yeah, smell the pits of your, even in the winter? Yep, you sweat all the time. So that water, the fact that it has a high heat of vaporization level, and when it evaporates, goes from the liquid to the gaseous state, brings a lot of heat with it, is very important for biological systems. We good? Okay, chemical reactions. There's some terms we just went over. Going to repeat. A chemical reaction happens when I take something, well, let's call it A, and I mix it with something else, let's call it B, and they come together to make something different. Let's call it AB. Yes? Is that the only kind of chemical reaction I can have? No. Sometimes I can take AB and I can do something to it and I can break it apart into A plus B. So we have to know some of the terms when we discuss chemical reactions because, yeah, believe it or not, we're going to talk about them a lot this semester. Even more next semester. So when I write a chemical equation, and we can see this at the bottom of page 35 in your textbook. It would help if I plug this in. There we go. We see typical chemical equations written as follows. Once I get the darn pen to work. Come on, pen. All right, maybe not. All right. Bottom of page 35. We have something that's going to react with something else. Remember my A plus B example? We call those reactants. And in this little equation that we see at the bottom of the page, I'm going to still play with this and hope that I can get it to, oh, there we go. A plus B gives me AB. Or in this equation here, what is it? In this case, it's H plus H, and H stands for what? Hydrogen. When they get close enough together, they're going to do what? They're attracted to each other. Why are they attracted to each other? Very good. They only have one what? Valence electron. And what do they want to be happy? They want two. So they're hanging out beside each other. What should we do? Bond. What kind of bond? A covalent bond. And that's going to give us some sort of product. So in this reaction, A plus B, what would we call those? The things that are going to react with each other, what do we call them? We call them reactants. In our example, it would be hydrogen and hydrogen. And when they get close enough to react with each other, they're going to form a product. So in this little example, A plus B goes to AB. AB is my product. Yes? So we have to know the terms reactants and products. And different patterns of chemical reactions are not all the same. So when we talk about chemical reactions, some things build things up. Some reactions break things down. Some reactions kind of mix things up in molecules. So the one I drew on the board, what kind of reaction is that? That's called a synthesis reaction or a combination reaction. And that makes sense, doesn't it? I'm making something new. So remember sodium and chlorine we talked about earlier? Na plus Cl equals, or goes to, I'm going to say goes to with my arrow, NaCl. What kind of reaction is that? It's a synthesis reaction. So I made salt from sodium and chlorine. So what are my products in this reaction? Yep, salt, sodium chloride. What were my reactants in the reaction? Sodium and chlorine. Okay? Chloride, chlorine. Okay? Everybody get that? And I'm making something new. That's a synthesis reaction. Well, what happens if I do this? Oops. Yep, that's called the decomposition reaction. So I'm breaking apart AB, and the result is A plus B. In this case, what's the reactant? AB. What's the product? What do I end up with? A plus B. Now, some reactions, we're going to see this. What's that mean? Nope. I put an arrow going that way and an arrow going this way. It can go back and forth. Okay? Until, and a lot of times what we're going to see is reactants and products in solution keep going back and forth until they create what we call equilibrium. So if I were to take a molecular snapshot of what's in the beaker, and we're talking A and B and AB, I might see an equal number of A's and B's by themselves and AB's with them together. And they're going to keep going back and forth like that. That's an equilibrium reaction. Now, some reactions break things apart, like the second reaction there, the decomposition reaction. When I'm breaking things apart, that is called a catabolic reaction. Think catastrophic, like a hurricane breaks apart buildings.
So that's different than decomposition, or the same?
Same. I can also have a reaction called an exchange reaction, or displacement. And if you look on the bottom of page 36, you'll see that guy. So we have AB plus C is what? AC plus B. You see what happened? So things got moved around a little bit. Again, the reactants are going to be on what side? The left side, and the products are going to be on the right side. If I put an arrow like this, I'm blind as a bat. What does that mean? It goes both ways. I have an equilibrium set up.
Is that considered a single displacement or double displacement?
That's a single displacement. Okay, if I had, is there an example? Yeah, the second example would be double displacement. Let me get my little hand up here. So if we have this, and what would that give me? What do we call that? It's still a displacement reaction, but now I didn't just change one thing, I changed what? Two things. That would make it double. Oh, that's cool. All right, I was just playing. Sorry. I wondered if I turned it upside down if it would become an eraser, and it does. All right, so we need to understand the patterns of chemical reactions described in your textbooks. Everybody understands what a reactant is. Everybody understands what a product is. We have different reactions like synthesis or combination reactions. We have decomposition reactions, which are also catabolic. What if I'm building something? That's called an anabolic reaction. Two other terms that we need to know when we discuss reactions of metabolism in humans are something called redox reactions, which is a combination of two different types of chemical reactions. Now this one's a little bit confusing because when I say I'm reducing something, you would assume what? I'm losing something. But is that the case? No. So, when I oxidize something, or a reaction of oxidation takes place, what happens? I'm losing electrons. And typically that means I'm losing a hydrogen ion. And guess what a reduction reaction is? I can see you all have read the chapter. What's a reduction reaction? Oxidation reaction, lose electrons. What's a reduction reaction? Gain electrons. So now you see why we have that little term redox? Because these reactions tend to couple up. If I'm losing electrons in one reaction, I have to gain electrons in the other reaction. It'd be nice if we could work hand in hand. We're going to see examples of redox reactions when we discuss cellular respiration, chapter 25, next semester. Okay? And we give off, or have the ability to give off and make quite a bit of energy with the coupling of an oxidation and reduction reaction. So those terms I need to know too, or as well. We're going to see it if you look on page 37 in this wonderful reaction called cellular respiration. C6H12O6. That's big. We're starting to get big now, right? What is it? Glucose plus oxygen, O2. When they come together and a series of many chemical reactions takes place, and you're going to learn them next semester, chapter 25. What is the result? ATP. Now, why is ATP so important? Yeah, that's your energy molecule. That's the reason you are as big and as complex as you are. That's the reason you have big, enormous cells with complex nucleus and complex membrane-bound organelles. Because you have the cellular mechanisms to make lots and lots of ATP. Okay? And that reaction of cellular respiration allows us to be as complex and advanced as we are. So we'll talk about it in details, chapter 25 next semester. We'll talk about ATP a lot, though. It's going to come up. So remember ATP. What does ATP stand for? It stands for adenosine triphosphate. The next thing in your book talks about energy flow in chemical reactions. And when I release energy from a chemical reaction, kind of like the one we talked about in last class when you made that volcano in elementary school, did that release energy? What kind of reaction can we also call that? It's called an exergonic reaction, an energy releasing reaction. Now, some reactions actually suck up energy, don't release it. They take a lot to happen. Usually anabolic reactions take up more energy than they give off. What do we call these guys? We call these guys endergonic reactions. So we need to know those two terms as well. Everybody with me? Good.
Can you say those again?
So an exergonic reaction, you're going to find this on the page, bottom of page 37 under energy flow in chemical reactions. An exergonic reaction gives off more energy than it takes to happen. And an endergonic reaction takes more energy to happen than it gives off or releases. Yes? Reversibility of chemical reactions, we already kind of touched on that. Chemical equilibriums can happen. Things kind of float back and forth between reactant and product in different solutions in an equilibrium reaction. If I add more to an equilibrium reactions, let's go to this one. If I add more A and B separately, this reaction is going to be driven to go faster in this direction. Does that make sense? If I add something to one side of an equilibrium reaction, in this case I add more A and B. Let's say I have sodium and chlorine. Got a beaker of sodium chloride. If I add more separate sodium and chlorine to the beaker, we're going to cause that reaction to be driven to the right. So all of a sudden I'm going to start making more sodium chloride at a faster rate until what happens? If it's an equilibrium reaction, what do you think's going to? Yeah, until I reach that, in this case, equilibrium again, which is balance or homeostasis. What if I add more sodium chloride to a beaker of water with just a little bit of sodium and chlorine in it? What do you think is going to happen? It's going to be driven to the opposite end until we reach a equilibrium. And when you put sugar in your coffee, you do that. Yes? And sometimes it takes longer, if it's iced coffee, to reach equilibrium, right? Am I making sense? Okay, good. So, yes? No? Where are we?
Like page 37.
Yep.
We're looking at the glucose plus the oxygen.
So we're looking at C6H12O6 plus 6O2. Is that the one?
Oh,
Yeah, if the number is subscript, that means in the molecule C6H12O6. Everybody know what that means? We have in this molecule 6 carbons, 12 hydrogens and 6 oxygens. But if I put a big number up here, what does that mean? It means I have 2 of those.
So you say like it'll be C12, H24, and O.
No. No, because that would be a different molecule. So if I have 2 sugar, let's call the sugar C6H12O6 sugar cubes. So if I have 2 sugar cubes, I still only have 1 sugar, right? No. I have 2 sugar cubes, separate. See the difference? In order to create a reaction that's going to give me a product, in this case, in order to create, and this is a whole balancing chemical equation thing, but in order to create this reaction, I have to have, for every glucose molecule, C6H12O6, I need to have how many oxygen molecules? 6 of them. Yes, ma'am.
So the 2 in the beginning means there's 2 molecules.
Of whatever's behind it. If it's a subscript, that means there's that many of those atoms or elements in that molecule. Yes, ma'am.
I think his question was trying to ask is what the difference is between O subscript 6 and that and 6 O2. You know what I mean? It's-
Yeah, that's. I think I just answered. Did I answer that?
Yeah, yeah, I was just putting it in other words.
Yep.
What he's trying to say. So it's, because it's all together, that's glucose and 6 O2, there's 6 oxygen.
Actually, there's 12 oxygens, but they're oxygen molecules,
Right.
so they're stuck together. But I need 6 of them. Yes.
Right.
Does that make sense? So the numbers, when you put that 2 in front, if I look at just the atoms, and you said this before, 2, there is in this 12 carbons, 24 hydrogens, and 12 oxygens. But remember, they're lined up to make a glucose molecule. Does that help?
So then there's 2 molecules.
There's 2 molecules of glucose, but if I look at the elements separately, there's that many altogether. Did that help? Kinda. Look at it again. See if it makes sense. You grasp it? Everybody else good? Okay. If not, ask the question. All right, what are some of the factors that can either increase reactions or decrease reactions? Well, they're listed, of course, on page 38 in your book. And think about molecules. Remember we talked about last class? Atoms, elements, molecules, everybody's in motion. So think about this whole room of people. And if I told you that you constantly have to be in motion in this room, imagine you all moving around in this room. And you have to be in motion randomly. So when, you know those little cars you used to have as a kid, or hopefully you lived vicariously through your children and got one for them, that you wind it up and it bangs against the wall, and then it backs up, bangs against the wall, then it backs up and bangs against the wall. You know what I'm talking about? Okay. Those fun toys, that's what molecules and atoms and elements do in nature. So they're in random motion, and when they hit a container or whatever they're contained in, they're going to bounce off and move in the opposite direction. So what speeds up the movement of these molecules? Heat. And if I speed up the movement of the molecules, I speed up the chance that they're going to do what to each other? Bang into each other. So temperature is going to increase the rate of chemical reactions. You understand why? So if I take this room and I fill up, not the seats that you see now, say I fill up all the seats, and then I tell you to bang around in the room, what are the chances you're going to bang into each other now? Is the percentage higher? So if I want to increase the rate of a chemical reaction, if I increase the concentration, is that going to do it? Yeah. If I have more things in my beaker, the chances that they're going to bang into each other are going to be greater. If I have my lonesome little sodium over there and my lonely little chlorine over here in this big, huge room, what are the chances they're going to bang into each other? Yeah, slim or none. It might take a very long time. So if I decrease the concentration of solutions, what am I going to do to the rate of reaction? Decrease. Particle size is also going to have an effect on your movement. Bigger things move what? They move slower. Smaller things move faster. And the faster I move, the greater the chance is that I'm going to do what? Smash into something else. So particle size can also contribute to reaction rate. And then what if I had like a little matchmaker molecule with my sodium and chlorine? Remember those lonely little molecules at the ends of the room? Well, what if I had a little matchmaker molecule that would grab both of them and bring them close together to react? Would that help? Get them together? That's called a catalyst. And what we're going to talk about in anatomy and physiology a lot is something called an enzyme. And what's an enzyme do for a living? It brings things together so they can react. Or it helps to break things apart. And it's going to do this very efficiently in many different systems in our body. And by doing it, it's going to help to reduce the amount of energy I need for reactions to take place. If I didn't have enzymes or catalysts in my body, would I be able to be as complex as I am today? No, because the reactions would not take place as quickly. So we're going to discuss many, many different catalysts. And again, they have that enzyme name that we're going to talk about a lot through the course. And we're going to help speed up chemical reactions and decrease the amount of energy it takes for those reactions to take place with a catalyst. All right, let's get into some biochemistry. Woo! Even more frightening. Now, two different divisions of chemistry. Organic chemistry, inorganic chemistry. I enjoyed taking both. Or biochemistry, or inorganic chemistry. I had to take them all. But what's the difference between the two? Any molecule that we're talking about that has carbon in it, we're going to talk about it in organic chemistry. And organic molecules tend to be very, very large. Organic molecules tend to form covalent bonds. Sharing, because we're so big. Yes? How about inorganic? Anything without what? Carbon. If I don't have carbon in me, I am inorganic. And inorganic molecules tend to form salts. Some of them are polar. Many of them are ionic. Everybody understand what I mean by that? Different kinds of bonding. Sodium chloride is an inorganic molecule. It's also called a what? What do you call it? You don't call it sodium chloride. Give me the sodium chloride, please. Pass the salt. So many inorganic molecules tend to form what we call salts. The first one they talk about is our big friend water. And again, water's properties are extremely important for biological systems. So we already talked about those already. I kind of skipped ahead a little bit. I'll review. High heat capacity. Why is that important for us? What kind of organisms are you? You have to maintain a core body temperature of 98.6 degrees Fahrenheit or 37 degrees Celsius. What do we call you? Warm-blooded organisms. So water and its wonderful high heat capacity and its high heat of vaporization level is going to help keep our core body temperatures at that wonderful 98.6 or 37 degrees Celsius. Yes? It also acts as a wonderful solvent because of its polar qualities and those wonderful hydrogen bonds. Most everything dissolves in water. Not every single thing. Anybody ever tried to make salad dressing lately? Add the vinegar, add the spices, add the oil. Does oil dissolve in water? No. It's hydrophobic. So not everything dissolves in water, but most things do. And we call it the universal solvent because of that. Layers of water throughout body systems in human body is going to help act as kind of like the oil in your car to help reduce friction so that damage doesn't take place in human systems. It also is going to allow chemical reactions to take place in it. Sometimes it's actually going to help me break things apart. And sometimes when I bring two things together, I make water. If I want to break something apart with water in a chemical reaction, guess what I call that? I'm going to use water to break something apart. Ready? Hydrolysis. Break the word up. Hydro, that means what? Water. Lysis means break apart. So hydrolysis reactions, we're going to talk about in a minute, are very important in living systems. Water can also help for the reaction to take place, and it's so important that many of the reactions of metabolism in my body produce water. So if I bring two things together by sucking out some water, that's another kind of reaction. Anybody know what that one's called? It's called a dehydration synthesis reaction. So break that word down. I sucked out water, dehydration, just like you put it in those little machines. You suck out the water of grapes and you get a raisin. Yes? So I suck out water to bring two things together. Synthesis reaction. And we're going to see that quite a bit in throughout this entire book. And then, of course, last but not least, water acts as a cushion. Watch this. Ready? No brain damage. How come? Yep. I got some nice cerebrospinal fluid in there. So when I move my head like that, I don't bang my brain up against the side of my cranium and cause brain damage. What happens when you do that really, really hard? You get a concussion. Is that good? No, that's very bad. And you do that often enough, and what's going to happen? Yeah, you're going to damage that very sensitive, delicate brain. So cushioning is a very important part of water's job, that wonderful inorganic molecule in our bodies. They talk then about salts. So salts, inorganic molecules, tend to form from ionic bonding reactions. Back to sodium and chlorine. What happened to sodium and chlorine, two neutral things, when they bonded with each other through ionic bonding? Well, we formed a salt, but now is sodium neutral and is chlorine neutral anymore? No, sodium has a what charge now? It's got a positive charge because why? I lost one of my what? Electrons. Now I have one more positive charge than I do negative charge. I form an ion. What's a positive ion called? Cation. Very good. We have to know that. And chlorine turns into an ion also. It's got a charge now because it did what? It gained an electron. So what is the charge on the chlorine now after that ionic bonding reaction? It's a negative ion. What do we call negative ions? An ion. Good. So these guys are floating around all over the body. We've got calcium ions, we've got potassium ions, sodium, chlorine, you name it, they're floating around. These guys are called electrolytes. And they're very important for moving things like electricity down the processes of all of your neurons. And they're also important for movement of molecules from one place to another. You don't have to write this down, and I hope I don't confuse you, but the reason you can get rid of water is because you can get rid of ions. So if I get rid of some potassium, which has a positive charge after ionic bonding, water is going to follow it. Why is water going to follow it? It's got a positive charge. Water is a what kind of molecule? Polar molecule. Water has a slightly negative and a slightly positive end. Well, if I'm potassium and I'm positive, I'm going to attract what? That slightly negative end of water. So that's actually how my body gets rid of excess water. It gets rid of excess ions, and water kind of tags along. It's called obligatory water secretion or reabsorption. Don't write it down. We'll talk about it, urinary system chapter. I don't know what it is. Second semester. Yes? So, electrolytes are very important for reactions of metabolism in our bodies. And imbalances in electrolytes in the system can cause all sorts of problems with I just lost my train of thought. Chemistry. So, ionic balance, very important in the body. The next thing the book talks about in the inorganic category, is acids and bases. Does anybody know what the definition of an acid is? A solution that has a high concentration of, or a higher concentration of, hydrogen ions in solution. So look at that little beaker over there. Molecule, water, made up of what? Hydrogen, two hydrogens, and an oxygen. What if I break off a hydrogen? And this happens all the time in water, beakers of water, just kind of hanging out. Sometimes, oops, we're floating around so fast, hydrogen might let go. What am I left with? I have a hydrogen, and now it's an ion because it left behind its electron. It's a positive ion, H+, and that extra electron that it left behind, what's left is holding on to it, OH, and it's got a charge. What charge does it have? Minus. Extra electron means extra what? Negative charge. So this happens all the time in water. And the concentration of these hydrogen, H+, and hydroxide ions, or hydroxyl ions, and we see this on the top of page 40, is how we measure pH. Now, here's the scary pH explanation. The definition of pH is as follows. The concentration in moles per liter of hydrogen ions in solution. That's right in your book, so you don't have to write that down feverishly. You can go back and listen to me again. Yes? So pH by definition, is the concentration of hydrogen ions in solution. So you see that chart over there? That's the pH scale. If the concentration of hydrogen ions, and what was that other ion I made when I threw something in water? Hydroxyl ions in solution are equal, my solution is neutral. And the pH scale for neutral is 7. Do you know why it's 7? Because by definition, now I want you to look at that column that says hydrogen ions. By definition, pH is what? What's pH? Concentration of what? Hydrogen ions in solution. In moles per liter. I threw that in there because it's in the scale and I want you to understand where it comes from. Yes? So you see why it's pH 7? Neutral. Now, on the pH scale, when I start to increase hydrogen ion concentration, which would be going where on this scale? Down or up? Down. Here's where the math part comes in. That's the reason why it's a prerequisite for this course, because we have to know a little tiny weeny bit about math. Yes? 10 to the negative 5. Is that bigger or smaller than 10 to the negative 7? It's bigger! Because it's closer to what? 0. This is negative exponential notation. So if I had lots and lots of chocolate and I said I'm going to give you 10 to the negative 5 of it or 10 to the negative 10 of it, which would you want? 10 to the negative 5, because that's more. Even though that wouldn't be nearly enough for me. Yes? I know. Okay? So what happens, now here's my next question, now that we understand the exponential notation thing. If the hydrogen ion concentration is greater than neutral, what happens to our solutions? They become acidic. Now, look on the other side of the scale. So go to the 10 to the negative 5th again, since we already mentioned that. If I have 10 to the negative 5 moles per liter of hydrogen ions in my solution, guess what I'm going to have of hydroxyl ions in my solution? 10 to the negative 9. Is that greater or less? It's less. See? So the greater the hydrogen ion concentration in solution, the more acidic my solution is. But here's the confusing part. What happens to the pH? The number gets lower. You see why? Because remember, what was the definition of pH? You can say it in a concentration of hydrogen ions in solution in moles per liter. Yes? So you see why the number goes down? The concentration is actually going up. On the opposite end of the scale, if the concentration of hydrogen ions is lower than the concentration of hydroxyl ions in my solution now is what? What's it say in blue? Basic. Very good. So if I go in the opposite direction with the hydrogen ion concentration, again, look at those numbers. Compare the numbers. If I have a concentration of 10 to the minus 10 hydrogen ions, that's moles per liter again, in solution, what do I have for hydroxyl? 10 to the negative 4. Which one's bigger? 10 to the negative 4. So in a basic solution, the concentration of hydrogen ions in solution is what? It's lower than the concentration of hydroxyl ions in solution. So if I take something like hydrochloric acid, that's very acidic, and I throw it into a beaker of water, it's going to dissociate. What's that mean? It's going to kind of come apart. Let me go back to this. So here's the formula. HCl plus H2O. So if HCl dissociates, it's going to form what in my water? I'm getting good at this. Well, and some of those are going to break apart too, right? Yes? See where I'm going? So what do we call hydrochloric acid? Is an acid because when it dissociates, it gives off more what? Hydrogen ions in my solution, creating a more acidic solution. And if I go down on the scale, we see that different substances will give off either higher concentration of hydrogen ions or higher concentrations of hydroxyl ions when they dissociate in solution. What if I put this in water? What's going to happen? You're all in a coma today. It's Thursday. You're not supposed to be in a coma on Thursday. You have to wait till Friday to have your coma time. So what's going to happen here? Can you see that? Oh, podium's in the way. Ah! Let me go up here. Sorry. Oops, shoot. All right, I'm just going to make the beaker now. See, I jinxed myself because I said I'm getting good at this. So this is what happens when NaOH, sodium hydroxide, dissociates, it's going to create that, and we're going to have some H2O in there, right? But of course, water's going to be at equilibrium, so we're always going to go back and forth between what? So where is there and you know there's many more molecules in there than just the ones I wrote. So we're in a basic solution, there's going to be a higher concentration of what? OH negative hydroxyl ions in solution than there is hydrogen ions in solution. Yes? So at the extremes in either scale, we can cause some problems in our chemical systems. So we have things called buffers in our body to help maintain proper balance of hydrogen ions and hydroxyl ions in our solution. pH can mess up chemistry big time. And it can mess up your chemistry big time. What is normal body pH? Anybody know? I'll tell you. It's 7.35 to 7.45. Pretty tight, huh? And it's got to be that way. The buffers are going to allow it to be that way. You see all this chemistry going on. We keep talking about all this chemistry going on. We're constantly making hydrogen ions and hydroxyl ions, breaking them apart in water. It happens all the time. So our buffer systems are going to help maintain that hydrogen ion concentration so we don't damage our cells. We don't damage our molecules that we make in living systems. So pH, and you can see a little reaction. I'm not going to write it down. You can see it on the right-hand side of page 41. Buffers are going to help maintain hydrogen ion concentrations by either sucking them up and creating molecules or doing what? If I'm getting low in hydrogen ion concentration, what can they do? Give them up into solution, and they're going to help maintain. We're going to talk about bicarbonate ion buffer systems when we talk about the respiratory system next semester, and I can't remember the chapter number. Okay? You with me? All right, so different types of reactions involving water. We see here biological molecules are formed from single building blocks. We call them monomers. Or break them apart in several different ways. With the help of water, can I move that up? Oh yeah. We can have something called the dehydration synthesis reaction. And what are we doing? Yep, we're sucking water out. So if I look at the chemical makeup of monomer 1 and monomer 2, there's a little OH on one and an H on the other. We're going to pull those out, bring them together, and water is a waste product. We're going to use that water for many, many different things in our body. It's called metabolic water, and it's a very important way to get water in the system. Water can also, when I add it to something, break things apart. What do we call those reactions? Hydrolysis or hydrolysis reactions. And now let's throw in some real life, and I don't think I can pull that down anymore. Oh, yep. Example of what kind of reaction? If I take that green one over there, what's the green one? Glucose, and I add it to another one. It's another sugar called fructose. And I suck some water out. I create table sugar. Yes? Sucrose. So sucrose is created by what kind of reaction? No, not hydrolysis. It's a dehydration synthesis reaction because I took two what? Two things, and let's apply our letters to them again. A and B, and I made, no, I made AB. Yes? Make C? That would be hard to make C. And what did I do in the process? I sucked out some water. Now, you go to the cafeteria, you take some sucrose, which is a combination. It's a disaccharide of glucose and fructose. And what do you do with it? You pour it in a cup, and you pour some coffee in it. Now what are you doing? You are breaking it apart with most of your coffee is what? So what kind of reaction is that? Hydrolysis reaction. So when you put the sugar in the cup and you spin it around in the solution, it's going to dissociate. And that is a hydrolysis reaction. Yes? So good, you get the chemistry down. Why does this keep doing this? Boy, I hate computers. All right, we're going to talk about very important organic molecules. Because now we're done with inorganic. Everybody has to understand salts, acids, bases, pH. Water. Okay? That's the biggie in inorganic. Now we're going to get into organic molecules. And organic molecules are huge. They're huge because they're formed on carbon chains. How many valence electrons does carbon have? What does it want to be happy? 8. It wants 4 more. That's a lot. So I'm going to do a lot of sharing. I'm going to do a lot of covalent bonding with other carbons and a bunch of other things to make these large molecules. Usually there's a lot of hydrogens in there, some oxygens in there, throw in a few nitrogens, And that's the basis of most of our organic molecules. A few of them have some different ones, but that's the basis of most of them. And the places in where these guys bond together create different shapes. These different shapes are going to react differently in the environment. So the first organic compound, very important group of organic compounds we're going to talk about are the carbohydrates. Give me an example of a carbohydrate. Pasta! Sugar. Yes? Bread. All carbohydrates in different shapes and forms. The monomers of carbohydrates, which are the what? The single unit building blocks, that's what a monomer is sugars. We have simple sugars. C6H12O6. But guess what? They're shaped different. Their C's and their O's and their H's are in a little bit different place. So they're going to react differently in a chemical reaction. Glucose, the green one all the way over there, everybody knows what that is, right? That's C6H12O6. Its neighbor, fructose, guess what? That's C6H12O6. What's the difference? Shape. Shape, difference, reactivity, difference. Chemical formula, same. Galactose, simple sugar, C6H12O6. If you don't believe me, count them. Every time there's a bend, there's a C, unless it's written. Deoxyribose, C6H11O6. It's missing an oxygen, but it's still a simple sugar. And then ribose, a little bit different as well, but still a simple sugar. So these are all monomers of the carbohydrate family. When I bring these monomers together in different combinations through what type of reaction? Dehydration synthesis reaction. Oh, chemistry people. I create something called a disaccharide. And you know sucrose very well. It's in the cafeteria. Anybody ever have a malted milk ball? Love those. Maltose, also a sugar. It's not as sweet, though, as sucrose, is it? Sweet to the taste. It's a little duller on the sweetness. But it's, how can that be? It's C6H12O6, C6. Why? Why? Because glucose itself, by itself, doesn't fire off as many sweet receptors as fructose, which fires off a little bit more. Fructose comes from what? Anybody know? Fruit. So it's a fruit sugar. And then we have lactose. Where's that one come from? Milk. Some people are lactose intolerant. Because in order to break that apart, galactose and glucose, by what kind of reaction? Hydrolysis. I need an enzyme to do that. Guess what the name of the enzyme is? Lactase. So if you don't have the enzyme, or, here's another kicker, you have the enzyme, but you made it the wrong shape. Is it going to work? No. So you can't break it down. You can't break it down. It's big, it's bulky, causes gas. Yes? Anybody who's lactose intolerant knows what I mean. And if I put a whole bunch of these monomers together to create very large molecules, and you do it all the time, we call that a polysaccharide. Now, some of you mentioned some carbohydrates here, like potatoes and pasta and bread. What do we call those? Are they simple? We call them complex. Why do we call them complex? because we have a whole bunch of monomers, whatever the molecule happens to be, stuck together to make a really big polysaccharide. You do this all the time. Every time you eat a carbohydrate, you break it down into its building blocks through what kind of reaction? Thank you. Dehydration? No. Break it down. Hydrolysis reaction, and then you take those little parts and you bring them together in other ways through dehydration synthesis reactions. One of these wonderful little C6H12O6s makes 36 to 38 ATP molecules after it's been manipulated in the cellular respiration reaction. You don't have to write that down. I just scared you, didn't I? So they're very important, carbohydrates. We need to eat them. Where do we get them from? Somebody who makes them. Who makes them? Plants. What'd you say? Mommies. Plants. Plants are your friends. Eat them every day because you need carbohydrates so you can make enough energy so your brain will work. Okay? So when we eat them, we take them in. We need them all the time at a constant level. So we bring them in. Some of them we use right away, but some of them we do what with? Store for a rainy day. Your liver, it's like the cabinet at home. You know, when you go home and you're really hungry, what do? You open the cabinet and grab the crackers. Yes? So your liver's like the cracker cabinet. You're going to store lots and lots of simple sugars in a big molecule called glycogen in your liver. That's a polysaccharide or a complex carbohydrate. All right, you guys lucked out because I was a little wordy today. But what I want you to do, because I'm going to finish this really, really fast, and am I going to give you a quiz on Chapter 2 in class on Tuesday? Yes. So I want you to finish Chapter 2. We'll finish talking about the rest of the, what kind of molecules? What kind of molecules? Organic molecules. We'll finish talking about them on Tuesday. Okay? Quiz Chapter 2 on Tuesday.